Welcome to the Picture Language Seminar. We're extremely happy today to have Klaus Fredenhagen from Hamburg. He's one of the leaders in algebraic quantum field theory, and with Detlev Buchholz has carried on the tradition of Rudolf Haag. And today we're going to hear about constructing algebraic quantum field theory. We're looking forward very much to your talk. So Klaus, why don't you share your screen?
Yes, I'll try. Okay, so thank you very much for the invitation to present these results here in this nice online seminar. So I want to talk about some new ideas on constructing algebraic quantum field theory. These ideas have been developed in collaboration with Detlev Buchholz, and this was the first part, and then was further elaborated in collaboration with Romeo Brunetti, Michael Dütsch, and Kasia Reisner. Now, so it's on quantum field theory, and we know that quantum field theory develops an almost complete description of fundamental physics. Unfortunately, gravity is not really included, but for other problems, it's almost complete. On the other hand, when you look more carefully on this, you see that there are still some severe open mathematical problems. And one can try to approach these problems from different sides. So for instance, by constructing simplified models, or one can try to just to postulate certain general axioms which the theory should fulfill and hope that these axioms fix the theory to some extent. Now, when you look at the physical relevant models in four-dimensional space-time, then at the end, you have to rely on some uncontrolled approximation, for instance, formal perturbation theory, or when you think of QCDs, then you would use some lattice approximations, but in general, you cannot control the validity of these approximations. And when you look at the axiomatic side, then there are some general, very non-trivial features like the spin statistics theorem or the PCT theorem. But this axiomatic characterization usually does not fix a concrete physical model. Now, for some reason, I cannot go to the next page.
Just
this. Okay, so I go outside of the full screen because for some reason it does not work. So here I just listened a few approaches to the construction of models, like the construction of the interacting Hamiltonian by constructive quantum field theory. This is the old approached by Clement Jaffe and others, and then later mainly put into the problems in the approach to construct the Euclidean path integral. There are models in two-dimensional conformal field series, and there are models with factorizing S matrices. But altogether, there remains a gap for the construction of really interesting models which can directly be applied to fundamental physics. Now, the new approach I want to present here consists in adding certain algebraic relations which are valid in formal perturbation theory to the axiomatic structure. And this relies on a certain reformulation of perturbation theory. This, first of all, the generalization of perturbation theory to generic Lorentzian spacetimes. This was based on fundamental insights of Radzikovsky and the use of microlocal analysis, and then further developed by Brunetti, Hollandswald, and myself, and others. And the other reformulation concerns the way renormalization is described. And here one follows the general construction put forward by Epstein and Glaser, and later developed by Storer and others, by formulating all the renormalization conditions in terms of formal S matrices. And at the end, you get a functor which maps the category of spacetimes to the category of C-star algebras, and which satisfies certain fundamental physical properties, in particular the property of causality, and causality in two meanings. One is that causally disjoint regions are independent of each other, and the other is that causally dependent regions are show the right way of dependence. Now, the models we look at here in the symbols case are just the model of a real scalar field. So we have the field configurations, which are just smooth real-valued functions on some globally hyperbolic Lorentzian manifold M, together with a Lagrangian density, which has the usual form, a kinetic term, and a potential term. And in this framework, we look at certain local operations, and local operations are just local interactions. So we add to the Lagrangian some additional interaction described by some functional of the classical field configuration phi, which has this simple form, a polynomial part, and some a change of the kinetic term, where this change of the kinetic term has to be sufficiently small in order not to destroy the causality properties too strongly. Now, for these S matrices, we require a few relations. One is the relation of causal factorization. So this means that the S matrix of F plus G is a product of the S matrix S of F and S of G, provided the support of F does not intersect the support of the functional G, the path of the functional G. And then this, the interpretation is that these operations take place one after the other, and this is described just by the ordinary product. This is a relation which was used since long ago in perturbation theory. And, but there is a second relation which characterizes the underlying Lagrangian. And this is the following formula. The S matrix of F is equal to the S matrix where you shift the argument of the functional F by some compactly supported test function psi. So f psi of phi is just f of phi plus psi. And you do the same shift with the Lagrangian, and then you look at the arising interaction, which is then called delta L of psi. And this equation is just has this formula. I think this formula is easily understandable if you have this picture of path integrals, and this just amounts to a translation in the field configuration space. And when you take the infinitesimal version of this equation, take the derivative with respect to psi, then you get the usual Schwinger-Dyson equation. And actually, we can show that in perturbation theory, this equation is just the integrated form of the Schwinger-Dyson equation, and it's also mathematically equivalent to the Schwinger-Dyson equation. Now, when you switch on an interaction, then your theory changes and your S matrix changes, and this changes in this framework described by these so-called relative S matrices. So you take the inverse of S of G times the S matrix of F plus G, and this is now the operation S of F under the changed interaction. So you add to the original action the interaction capital G. Now, then you can look that these new S matrix, the S matrix S index G, satisfies the corresponding unitary field equation, namely, just by inserting the definition, you get this equality written here. And you see the additional term is just the shift of this additional interaction G. So by this operation, you describe the theory with a changed interaction G. But of course, you want that the new theory again satisfies the causal factorization. And then you need a slightly stronger condition, which is called here stable causal factorization. Namely, you require the following equalities, that S of F plus G plus H is S of F plus G, S of G to the minus 1 times S of G plus H, provided the support of the functional F does not intersect the past of the support of H, where now the past has to be considered relative to the new interaction, because the interaction might change also the causal structure. This is this condition. Actually, this condition is already discussed in the famous paper of Epstein-Glaser, but it did not play such a big role in perturbation theory, because in perturbation theory, this relation follows already from the simple factorization relation. But when you use these, as we do it here, these S matrices as abstract unitaries, just satisfying certain relations, then this is an additional condition. Okay, now we can define algebras of local observables by the following conditions. So we have some globally hyperbolic subregion of the space-time M, and the algebra of local observables in N, or theory with a Lagrangian L, is just a C-star algebra freely generated by unitaries S of F, where F is a local functional, as described before. There's a support F in this region N. And this is a free algebra modulo these three conditions. So you require stable causal factorization, you require the unitary field equation, and you require in addition that the S matrix for constant functional is just a phase. So it's just e to the I times c if this is a functional which takes on all field configurations the value c.
Why do you impose the third condition?
What was the question?
Why do you impose the third condition that for the constant functional you have to have the
The stable
exponential
causal
IC?
factorization. Yeah, this is just the idea I explained before, yeah, that the S matrices describe operations that take place one after the other.
Yes.
This is this condition, yeah? And this is the field equation which characterizes the dynamics. And this is just, these elements would be central anyhow, but it's convenient to assume that these are just phases.
Oh, okay.
Okay, now this seems to be very harmless, but there is a non-trivial consequence of these axioms, namely look at the following situation. So we take a Lagrangian, which is second order in the field phi. So it's a free Lagrangian, a free theory. And then we look at a certain subalgebra, namely the subalgebra generated, this is the algebra A1, is generated by functions S by S matrices S of F, where the function F, capital F, is a linear functional of the field phi. And then one can show that this algebra is isomorphic to the Weil algebra, namely the C algebra generated by unitaries W of F, which satisfies the Weil relation W of F times W of G is some exponential, some phase factor times W of F plus G. And this phase factor is just obtained by applying the difference of the retarded and the advanced green operator of the field equation to one of the test densities G and then integrating with the other test density F. This is a usual Weil relation, and this Weil relation here comes from these conditions I mentioned before, the causal commutation relation, the causal factorization condition, and the unitary field equation. In particular, there is no condition of canonical quantization needed. So the canonical quantization is a consequence of the causal relations. So this is also interesting in the following sense that it seems that this difference between future and past is directly connected with the non-commutativity of quantum physics.
Could I ask a question? Is locality a consequence of causal factorization?
Yeah. The reason is the following. When two regions are space-like to each other, then they fulfill both conditions. So the one region does not intersect the paths of the second region, and vice versa. So you have this causality, causal factorization in both directions, which means that the S matrices commute in these cases.
Can I also ask a question?
Yeah.
Conversely, if you have the Weil relations, can you construct all the data from before?
The Weil algebra satisfies these conditions.
Yes, but do you then also reconstruct the L and the S from the Weil algebra?
Yeah, for the linear functions, yes. These algebras are isomorphic.
Okay.
Yeah. Okay, now we can construct a quantum field theory in the sense of a local covariance as defined in the work of Brunetti, Ferch, and myself. So in this following sense, we have a functor from the category of manifolds. The manifolds are equipped with Lagrangians, and these Lagrangians have this standard form that they have normally hyperbolic Euler Lagrange derivatives, and they are the manifolds are globally hyperbolic with respect to the underlying metric. And this is a functor into the category of C-star algebras. And this functor is just defined in the following way. So we have these, the objects of these categories are these pairs of a manifold and a Lagrangian. And we associate to this pair a certain C-star algebra, A of ML. And the morphisms, so the homomorphism from ML to M prime L prime, are just given by embeddings of M into M prime, which interpolates the Lagrangians. So the pullback of L prime is just L. And the corresponding map between C-star algebras is given by this map where S of F is applied to S of the transformed F. The transformed F is just obtained by composing the field with this embedding chi. And you can check that all the relations mentioned before remain valid. So this is really an isomorphism of, yes, this is a homomorphism of algebras, of C-star algebras. Now, the question is, how far is this from ordinary quantum field theory? So let's again first concentrate on the Weil algebra. So the Weil algebra is, of course, well known. We know that it's a simple algebra, and it satisfies the time slice axiom. The time slice axiom says that the algebra of a neighborhood of some Cauchy surface of the total manifold M is already the full algebra. So from the axioms, first we would see that it's a subalgebra, but one can prove that it's already equivalent, isomorphic to the, identical to the full algebra. But this is no longer true for the full algebra when you admit functionals which are not linear in the field. Actually, there, this algebra has a large class of automorphisms. They act trivial on the Weil algebra. They respect locality, so they map local algebras into themselves. And they are of the form that the S matrix S of F is applied to the S matrix of some new functional, which is called here Z of F. And Z is a map which maps local functionals to local functionals, acts trivially on linear and constant functionals, preserves the support, and satisfies certain relations, namely satisfies this additivity relation written here. So Z of F plus G plus H can be decomposed in such a sum, set of F plus G minus set of G plus set of G plus H, provided the support of F and the support of H have empty intersection. This preserves the stable causality condition. And then there is a condition concerning the dynamics. So when you apply Z to this expression which appears in the unitary field equation, F index psi plus delta L of psi. This is non set of F shifted by psi plus delta L of psi. And if this condition is satisfied, then the unitary field equation is respected. So this is really an automorphism of the algebra. And one can easily give examples, so it's clear there are non-trivial such automorphisms. Now, this group is similar to a group which is known in perturbation theory as renormalization group in the original sense formulated by Stückelberg and Petermann long ago. Just the ambiguity which you have, which you find in perturbation theory when you want to define the time-ordered products for those expressions where in the naive approach divergences appear. So then you can ask yourself, is there a consistent definition of time-ordered products, and there is a certain ambiguity. And this ambiguity is described in terms of a certain group of transformations, and this is the renormalization group in this sense. And nowadays, renormalization group is mainly used in the sense given to it by Wilson, which is slightly different, but it's related, but not identical. So here it's really the renormalization group in the original sense of Stückelberg and Peterman, which here in our approach also induces these large class of automorphisms of our algebra. Now, how can we try to deal with these additional symmetries? Now, for this purpose, we looked at symmetries of the configuration space. So in this, our simple case, this configuration space is just a space of real functions. So we have symmetries which are given by diffeomorphisms of the manifold and multiplications by real numbers. And so this is the transformation of the configuration space, and we can look what this transformation does on our S matrices. So we define a certain map, alpha index G, which maps S of F to S of G star F. It's just the action of the symmetry on the functional F. And we see, this is straightforward to see, that this provides an isomorphism from our algebra to the algebra with the change Lagrangian. Yeah, this transformation is not a symmetry of the Lagrangian, it's a non-trivial change of the Lagrangian. Now, but here I restricted myself to diffeomorphisms which are compactly supported, and for functions, multiplication by functions which are equal to 1 outside of a compact region. Which means that the difference of the two Lagrangians, the new Lagrangian and the old Lagrangian, is compactly supported. So we have a compactly supported functional delta GL, and we can, instead of looking at the transformation of observables, also consider this change of the Lagrangian as an interaction. And so we can use this construction of relative S matrices to add this energy to this interaction to the original theory. And this provides it gives an automorphism of the algebra of G star L into the algebra with the Lagrangian function L. So we have two maps, one from the algebra with Lagrangian L to the algebra with Lagrangian G star L, and second map which goes back. So altogether we have an automorphism given by this formula here. S of F goes into S of delta GL to the -1, S of delta GL plus G star F. This is now an automorphism of this algebra. And we can compute this automorphism on linear functionals, capital F. And there we can compute that this automorphism is trivial. Okay, so this motivates the following postulate, namely, we require that this automorphism is just of the form discussed before for the renormalization group. So we postulate that to each such symmetry G, we have a certain element of the renormalization group, and this automorphism just acts in the same way as this renormalization group transformation, zeta G. And we call this the unitary anomalous masterword identity. Now, there are, of course, some consistency conditions which have to satisfy it. So this map has to satisfy a certain co-cycle relation, which is written here. So if you apply product of transformations, the corresponding renormalization group transformation zeta GH can be obtained as a composition of two other renormalization group transformations, and zeta G with upper index H is just the renormalization group transformation changed by this symmetry H. H acts in the following way on a functional, just by transforming the functional and adding the change of the Lagrangian.
May I ask a question?
Yeah.
In what sense is the word identity anomalous? Like, what kind of quantum anomaly does it contain?
Can you repeat your question, please?
What kind of quantum anomaly does this word identity imply? That's what I'm curious about.
Yeah, this is a kind of anomaly. Yeah.
In what sense? What sense is it anomalous?
So the simplest solution to the for this co-cycle addition relation would be that this is the identity. Yeah,
Okay.
And then you can make certain equivalence transformation with this co-cycle. And you can then look at equivalence classes of co-cycles. And if the co-cycle is not equivalent to the identity, then we call it an anomaly.
Oh, I see.
Oh, again, we check these findings in perturbation theory. So we prove that it holds in formal perturbation theory. And there it appears in infinitesimal form in the so-called anomalous masterword identity, which was postulated by Brenneker and Deutsch, and which can then also be seen in the Bartolini-Wilkowiski formalism. This was in terms of the so-called quantum master equation. This was done by Kasia Reisner and myself. And moreover, it's more or less equivalent to the Vesomino consistency relations. Because again, this depends on the formalism you use, so one has to make this precise. But this was analyzed in this paper by Ronetti, Deutsch, and Reisner and myself. So in this sense, we do something which is valid in perturbation theory, but can be formulated in this abstract C-star algebraic framework.
So if your master word identity is equivalent to the BV formalism, then is it able to describe some quantum chiral anomalies like the instantons? Chiral anomalies such as instantons?
Yeah, I come to this. Okay. Okay. So now let us assume that we have fixed such a co-cycle zeta. Then this characterizes a certain ideal in the algebra. We can take the quotient, which is on now the algebra A, M, L, and zeta, and we can look at the local subalgebras. So what we obtain is a certain Haag-Kastler net of local algebras, which is called here A with index ML zeta, which associates to each subregion a certain algebra. And now it's now interesting to analyze the properties of this Haag-Kastler net. And what was a great surprise for us is that this already satisfies the time slice axiom. So all these ambiguities in the time evolution disappear once this co-cycle is fixed. Another consequence is that you find a kind of Noether theorem. So you see that the symmetry, if you have symmetries of your Lagrangian, then they give rise to unitaries which implement locally the symmetry up to renormalization group transformations if there are anomalies. And if the anomalies vanish, then the classical symmetries coincide with the quantum symmetries. And moreover, when you have symmetries of the Lagrangian, and then the theory nevertheless changes because the co-cycle will in general be not invariant under the symmetry. So you see that the symmetry of the Lagrangian acts non-trivially on the co-cycle, but you can then go to an equivalent description where the co-cycle is essentially the original one, but instead the Lagrangian is changed. So what you see is the phenomenon which is known in perturbation theory is running coupling constants. So for instance, when you use scaling transformations in theories which are where the Lagrangian is scale invariant, then you can see under certain conditions such a non-trivial change of the interactions. Okay, so let me try to give at least an idea of the proof of the time-slice axiom. So we consider first a special case. Namely, let L be a stationary quadratic Lagrangian, so a free theory. And we look at diffeomorphism, which is compactly supported, and which acts in some region, O1, as a time translation by minus tau. Then we can look at the region O2, which is just the intersection of O1 and O1 minus tau, and see that the change in the Lagrangian, delta chi L, intersected with O2 is empty. Because the Lagrangian, by definition, by assumption, is stationary. Then we take some functional f, which is supported in O2. We apply the unitary anomalous Ward identity, which tells us that S of f is S of delta chi L plus chi star f. Now, in particular, when we take f equals 0, we see that S of delta chi L is S of 0, which is by assumption equal to 1. Now we decompose delta chi L into two parts, H plus and H minus, where H plus does not intersect the past of the region O2, and H minus does not intersect the future of the region O2. So then we can use the stable causality relation in this equation here. So we have this factorization between H plus and chi star f, and get the following factorization: S of H plus plus H minus, S of H minus to the minus 1, S of H minus plus chi star f. Now, H plus plus H minus is delta chi L. So this is just, then the corresponding S matrix is equal to 1. But then in the next step, we can apply this factorization to this second factor, this last factor here, and get finally this formula that S of f is equal to S of H minus to the minus 1, S of chi star f, S of H minus. Now, chi star f is just f shifted by minus tau. So we move f was at some time amount of time into the past, and this is implemented by some operator which does not intersect the future of the region O2. So we see that inside this region O2, the time translation is implemented by unitaries which are localized outside of the future of the region O2. Now we have some freedom in choosing this localization, and we can iterate the argument, and we can also go into the other direction if we use the time reverse situation. And if you put all these pieces together, at the end, you find the time slice property. And of course, this was for special Lagrangian, namely Lagrangian, which was stationary.
Excuse me. What is the time slice property?
The time slice property means that the algebra of the neighborhood of a Cauchy surface is the same as the full algebra. Yes, and it relies on the possibility to express the observables in some region by observables in the near to the given Cauchy surface. So you just need to transport. You need equalities of this form. Yes, in the simplest case, you would just take the Hamiltonian and move it to the Cauchy surface. Now, what happens if here we assume that the anomaly was trivial. Yeah, so we don't have this transformation, this renormalization group transformation on F. But this would, if there would be a non-trivial anomaly, this would not be a problem, because for two reasons. One is that the supports are not changed by the anomaly by definition. And the other reason is that we assumed here a quadratic Hamiltonian. And for quadratic Hamiltonians, one can show that then this change delta chi L is also quadratic, and the corresponding action of the renormalization group gives just a constant. So this would make no problem for this equation here. So it would just be a phase factor here, but the localization would not change. Now, when you go from this stationary case now to the non-stationary case, then this can be described by adding an interaction, because all the changes of the underlying metric can be described in terms of interactions. But this was an argument put forward by my student Bruno Kilian and myself some years ago, that there in the framework of formal perturbation theory, but it was a purely algebraic argument, that if the time slice axiom holds for the free theory, it holds also for the interacting theory. Okay, so I come to summary. So we have seen that the algebraic construction yields a definite algebraic quantum field theory in the sense of associating C-star algebras to regions. And it satisfies the axioms of locality, covariance, and time slice. It is fixed by two ingredients, the classical Lagrangian, L, and in addition, the fixing of this cocycle zeta, which characterizes the anomalies. And the cocycle relation corresponds to the Vesomino consistency conditions of perturbation theory. Now, this was a simple example of a real scalar field. Now it's straightforward to extend it to a finite number of scalar fields. We can also do fermionic fields, but there one has to add auxiliary Grassmann parameters in a consistent way, which is not completely trivial, but was done in another paper. Now, when you define some algebraic object in terms of relations, then it's of course always important to see whether there are some additional consequences of the relation so that maybe everything collapses afterwards. But here we are in a good situation because the algebraic structure is already present in perturbation theory. And there we know that there is a non-trivial representation in the sense of formal power series of Hilbert space operators. So the algebraic relations can certainly not collapse. And we can also check whether our constructions, how our constructions are visible in perturbation theory. And we see that the scaling anomaly for massless scalar fields just appears, and also the axial anomaly for massless Fermi fields are recovered in this formalism. In addition, one can ask the question whether these algebras can be represented in Fock space. And this is, of course, not at all guaranteed, but in some cases it can be shown. And this was done by Detlef Buchholz and myself for quadratic functionals. For quadratic functionals in 4 dimensions, one can show that this algebra can be extended, it can be represented on Fock space. Actually, it's also not trivial because what the non-trivial point is that these corresponding S matrices have certain phase factors, and our construction of these phase factors shows that the relations can be satisfied, but we could not prove that they are continuous. So this is also not completely satisfactory from this point of view, but at least they can be, one can find phase factors which satisfy all the relations. There are, of course, a lot of open problems. So the most important open problem is that gauge theories are not yet included. This is related to the fact that these gauge theories have these additional symmetries, which are completely local and would destroy the structure that we have here. Of course, there are ways to deal with gauge theories using gauge fixing, Fadeev-Popov goes, the Bartalin-Kubicki antifields, and so on. But these additional ingredients are a little bit in conflict to the C-star algebraic structure. Similar situation we had when we included Fermi fields. So probably one can do something similar here with these fields, but it has not been done at the moment. Another open problem is the problem of these representations of this algebra. Of course, it's a C-star algebra, so we know there are faithful representations, but we do not know much about the state space. In particular, we don't know its physical interpretation. We would like to see whether there are vacuum states or KMS states or whatsoever, but this is unknown at the present. And of course, what we expect is, because our model include models for which in constructive field theory it was shown that they don't exist, like 5⁴ in 4 dimensions. Here our interpretation would be the algebra exists, but it does not have a vacuum representation. Yeah, so the non-existence problem of constructive field theory would reappear here as a problem of finding, for instance, a vacuum representation. of a given algebra. And another problem is that in this approach, the zeta, this anomaly function, is completely free. Any co-cycle can be chosen, and all these answers were independent of the choice of zeta. But in perturbation theory, we know, this is Stora's main theorem of renormalization, that the equivalence class of the co-cycle should be fixed. And they are fixed by additional structures which are present in perturbation theory. And for instance, the existence of a vacuum, the fulfillment of the spectrum condition, and so on. And so in this algebraic approach, it's not clear how to incorporate the spectrum condition. So one possibility would be that fixing this equivalence class of this co-cycle is in some sense related to the fulfillment of the spectrum condition. But at the moment, this is a conjecture which has not been proven. Yeah, I thank you for your attention and conclude my talk with these words.
So thank you very much, Klaus, for a very interesting talk. And I'm sure this will lead to a great deal of discussion. So I'm going to end your screen sharing and hope that people will turn on their video when they talk to you directly. So let me ask a first question. If we go back to my favorite 5/4 theory, if you don't have the spectral condition, we know that the theory can develop singularities. So how do you what would be the way to distinguish dimension 3 from dimension 5?
Yeah, so I think the problem is really whether the so here so one thing I should say here, the algebra is always the same. Yeah, we construct a theory which is an extension of the Weil algebra. Yeah, but all these functionals can appear already in the free theory. So the interpretation as an interacting theory comes from the association of local subalgebras, but the total algebra is independent of the interaction. Of course, when you ask for the vacuum representation, this depends, of course, on the choice of the interaction, because since the dynamics depends on the interaction. Yeah, but the original algebra is always the same. And yeah, I think it's like in the naive interaction picture. Yeah, there you have your time zero algebra, and you can choose any Hamiltonian you want. Of course, this is in general a problem in relativistic quantum field theory, but in this functional formalism, this is also true here. And you see it in perturbation theory. In perturbation theory, it's completely satisfied, this condition.
But even in classical theory, when you don't have stability, then the solutions develop singularities in a finite time. And so maybe you're not on a smooth manifold.
Yeah, so that's of course here you define this in terms of ideals. So this you can also do in classical field theory, where you have your functionals and you have an ideal generated by the field equation, and the quotient is just a well-defined object. The question is whether the quotient can be characterized directly in terms of solutions.
Yes.
Then it could happen that you have singularities in solutions, but this quotient is well defined. So it's like in what you do when you characterize in algebraic geometry surfaces. Yeah, you define them better in terms of quotients than in terms of directly giving the coordinates.
So did Voronovich have
That's a better structure.
Yes.
And this is the structure we have here, the structure of the quotient.
I thought that Voronovich had a question.
Who?
Maybe not. Jörg.
So if you look at different Lagrangians, can you show that the C-star algebras you construct are in some sense inequivalent?
No, they are equal.
No, I mean, locally.
Locally, they are different, yes.
And how is that shown? For example, if you think of the triviality theorem for phi to the fourth,
Yeah.
it's conceivable that it turns out, after all, that even the local algebras of the phi-4 theory are equivalent to a free field if you go to dimension 4 or more. That's what one would expect.
Yeah.
I mean, it's a little too formal for my taste, this whole thing. One doesn't know what one is talking about. I also didn't understand how, for example, field strength renormalization and charge renormalization, how all that comes into the picture.
Yeah. Okay. So first of all, concerning the equality in this, so these are abstract C-star algebras which we construct. Yeah.
Yeah, very abstract.
Yeah. No. Just the C-star algebra. So it's but you can represent a dense subalgebra, namely the algebra generated by these S matrices in perturbation theory.
No, but.
And there you see that these are just algebraically different objects for the different.
Yeah, but let's now try to think not perturbatively, but non-perturbatively, if you permit.
Yeah, but these are algebras. So in these algebras, these are different objects. It's just not the same element. Of course,
No, but
it could be
if
that
I
you
think
have
of phi to the fourth, and I
could have a
construct my vacuum
representation.
representation in dimension 4 or more,
No.
then it tells me that the field is a free field. Now I can construct the local algebras for this free field, and it's the free field algebra. So apparently it's not the same as your algebra, or what?
Yeah, so what could of course happen is that you have a quotient. When you that the representation you construct is not faithful. So then of course differences can disappear. Yeah, so it could be that if you try to extend the representation, say the Fock representation, to this larger algebra, including functionals like phi to the 4, that such an extension is just not a faithful representation of the abstract algebra. Yeah, so this is a possibility. We cannot exclude this at the moment because we don't have control on this extension of the Fock representation. This can be done only in good cases up to now. Yeah, it's just so what one can construct is some larger object, some induced representation, but these are huge objects. But if you try to extend the Fock representation to these larger algebras, then it could be that this is not possible, or possible only in the sense that there's a large ideal.
Is there any number you can compute in the end?
No.
No. Actually, when you look at these anomalies, yeah, then of course these are the ordinary anomalies. you can, of course, we cannot compute them because this is an additional ingredient. But one could use the anomalies known from perturbation theory and try to use them in the definition in this abstract version. And then you get the usual answer. So you can directly compute these what I call running coupling constants. So looking at the change of the Lagrangian in terms of these anomalies. Of course, you have to, in our frameworks, the anomalies are an input. Yeah, we cannot compute them.
So I think she has a question.
Yeah, so if I was understanding correctly at the beginning when you constructed these, what you call the S matrix, you're only exponentiating integrated not all the local operators, but I guess what I would call either marginal and relevant operators. Am I understand this correctly?
So what was you mean these functionals we considered, or?
I mean these things you call the S matrix, or essentially the way I understand it, the way you call the S matrix is like you're deforming the coupling. I mean speaking from in the usual physicist terms, right? You're deforming essentially the coupling in your Lagrangian in a coordinate dependent way in some region of the space-time.
Yeah.
But it seems to me that the deformation you are considering is not the complete set of local field operators in the sense that Weizmann, well, not the way, not what you usually call the local field operators, but only the ones of sufficient low scaling dimension. For example,
so we looked here at functionals which depend on the field, and we admit also a contribution which depends on the derivatives, but this has to be of a special form so that it's again gives rise to a normally hyperbolic Euler Lagrange operator.
Right. So I think this is relevant to the question that were previously asked.
So the theory can be nonlinear, but the term involving derivatives must have the form of a normally hyperbolic operator, because otherwise we get into conflict with the causality.
So I think this is relevant to the question that were previously asked, a couple of questions that were previously asked, because this is very special to the what theory you're considering, right? It's not like you're just exponentiating all the possible local operators. You're looking at specific types.
So that's right. So we need to restrict the functionals. So actually we can, if you look at the relations, we can also restrict the degree of the polynomials. So we could, for instance, as I described, I can restrict oneself to linear or quadratic functionals, or in other applications, you would, for instance, when you want to discuss 5⁴ theories, you would restrict your degree up to 5⁴ up to the fourth order, and you have to be very careful in admitting terms with the derivatives, because then the character of the differential equation would change.
So I just have a small comment. I mean, I don't know much about this whole algebra of such operators, but in terms of property of specific operator this type, it seems that when you exponentiate integrated smeared operator in the kind of time order way, you can capture contact terms that are relevant for anomalies, various kind of 12th anomalies. You can contain contact terms which are hard to see in Weizmann functions, but can be seen in principle in kind of a sloppy physics language, the contact terms in time order correlators. That sounds closely related.
Yeah, but this is implicitly contained in this framework. So,
yeah.
So when you what usually is done is that you expand these. So these S matrices correspond to time-ordered exponentials of local functionals. And when you expand these time-ordered exponentials, you have all the products of time-ordered products of fields. And so these are just the usual, if you expand it, the usual Feynman diagrams. You have the usual problems of renormalization of Feynman graphs. And there you see all these structures, yeah.
Thank you.
So Mitchell, you have another question?
Yes. So I have under the impression that you're starting from the free theory and develop the perturbative series. But yes, back to the 5-4 theory in four dimensions. It is known that the 5-4 theory in 4 dimensions is not asymptotically free. So so I think the algebraic approach, which starts from the free theory and develops based on the perturbative methods, does not seem to apply to the 5-4 theory in 4 dimensions. Four dimensions. That's what I think. What could you tell me your opinion on this? Like, that's what I have been motivated by the book Beyond Conventional Quantization by John Clauder.
Oh, yeah.
I believe that there's non-trivial theory, 5-4 theory in 4 dimensions, but that should not be based on free theory. Because we are in the straitjacket of starting from the free theory and 5-4 theory in 4 dimensions is not asymptotically free. We cannot really get a non-trivial theory, and we are faced with the problem of triviality. That's what I think. So
yeah,
I think.
Okay.
So can you tell me your opinion on this?
I must say I don't know whether this is so. Here we are, as I tried to explain, very near to perturbation theory. So we see the structure we have in perturbation theory.
And okay,
but on the other hand, in the formulation, perturbation theory is not used, because in the relations we don't appeal to the free theory. We can in the relations the full Lagrangian appears. So it's in this sense independent of the splitting into free and interaction part. And so far, I don't see that this approach of Clauder would give a different picture here.
what I mean is that
it's very near to classical field theory in some sense. Yeah, so of course it could be that quantum field theory is so different from classical field theory that this analogy does not help. But it's a structure which you can describe explicitly. That's the nice feature of this. And there are these problems of finding good representations. That's at the moment we cannot answer.
So I think I should ask if there are any other questions, because we have a lot of experts here who have not said a word. And it's too bad that Detlef can't speak because his microphone is not working. Well, if there are no other questions, then I'll thank you again, Klaus, for a very fascinating talk. And we'll look forward in the future to developments with new examples, and look to the upcoming papers. Thank you. Thank you.
Okay. So
see you again next week.
Thank you for your attention. Ah, Christian.